It's 2024 and, well, 10 cents just doesn't buy you much anymore. You can get about 4 fluid ounces of gasoline, maybe 1/2 of one hamburger bun, half a gigabyte of SD card space from a reputable manufacturer, a minute and a half at Disney World, which you'd almost certainly spend waiting in line. The point is, 10 cents doesn't go far. But 10 cents can buy you this. This is the Puya PY32, a full-fledged 32-bit reprogrammable flash-based microcontroller with a Cortex M0 Plus core. Now, if we're really being semantic, I paid a smidge over 11 cents for this one, but there are other package options that are available for under 10 cents each if you buy 500. No matter how you slice it, these things are cheap. In this video, I'm going to give you a brief overview on these chips, and then walk you through setting up the software development environment. I'll cover the tools I'm using to program these, and then I'll flash a couple of test programs to show you that these do, in fact, work as described. I'm Zach, and you're watching Zach of All Trades. The point of this video is to show you how easy it is to get started with these, not to be an in-depth guide. I am not a microcontroller expert, or embedded software for that matter, but that should be encouraging to you, because if I can do this, you can too. First, I'm going to spend a few minutes discussing the PY32 in general. If you're already familiar with these, jump to the Getting Started with MicroVision section. So when would you want to use a 10-cent microcontroller? While saving money would be great all the time, these do have limitations. For one, 10 cents buys you a bare chip. You need a circuit board, a programmer, a couple of passive components, and then you need to solder it all together. Puya does have some development boards available, but they're very basic, without built-in debugging, and they're a bit pricey for what they are. Additionally, these are not powerful chips. Certainly faster than, say, an original Arduino, but not compared to some of the other 32-bit parts out there. There are going to be cases where these are just too slow, or they don't have all the features you need. Additionally, the software tools and online support are pretty much non-existent. To develop with these, you'll need to be comfortable researching issues yourself and capable of parsing datasheets and reverse engineering the provided example projects. So most of the time, if you're building one or two of something, you're much better off just buying a fully featured development board. Something like an Arduino or Raspberry Pi Pico, any of the popular options. These have well-established development tools, plenty of documentation, and lots of online discussion. But what if you need to make a lot of something? Let's compare this 10-cent PY32 to the cheapest STM32 part, which is around 70 cents, or the 80-cent, but far more powerful, RP2040 from the Raspberry Pi Pico. Take the example where you're creating your own product that needs a small microcontroller. If you hope to sell 10,000 items, then using this 10-cent part versus a 70 or 80-cent part will put about $6,000 more profit in your pocket. And this, of course, scales linearly, so if you're going to make $1 million of something, using this would put $600,000 more in your pocket. This is why companies spend loads of time optimizing their bill of materials cost, even just to save fractions of a cent on a part. The benefit I see for those of us not selling things is that having a chip this cheap allows us to build projects that need hundreds of microcontrollers. Say you're needing to detect something like temperature, sound, maybe motion, across a large area using hundreds of sensors. You may be able to find a smart sensor with an interface that would allow this, but if that doesn't exist, or if it's cost prohibitive, then you could take one of these cheap microcontrollers and turn that dumb sensor into a smart one. You can add custom processing at the sensor to perform data simplification, say by detecting a temperature threshold being crossed, or perhaps performing a Fourier transform on a signal and just returning the frequency content. Using this, you could do most of the processing at each sensor, and only notify a larger central processor if something interesting occurs. This will greatly reduce the demand on the bigger central processor. This approach is exactly what I'm doing on my LED tile backsplash project. I'm making several videos on this, and they're linked in the description. Be sure to subscribe to stay up to date on this project. I'm using these PY32 microcontrollers to read a microphone signal. I'm then calculating the largest signal amplitude, and then returning that value to a central processor at a specific time. Nothing was available off the shelf, and I needed 150, maybe 200 of these, so whatever I did had to be cheap, or this would have been way too expensive for a DIY project. Another potentially big benefit of the PY32 is that it natively runs at 5.5 volts. Not just the 5-volt tolerant inputs you get on some of the other microcontrollers. This means you can largely do away with level shifters, although I should note that this does come at the expense of a little higher power draw. I also feel like I should note that this isn't the only extremely cheap microcontroller out there. There are parts as low as 3 cents, although these tend to be 8-bit parts and one-time programmable. There's also the CH32V003. This is a RISC-V part that is around the same cost and actually seems to be more popular. There are more development board options for these, but bare chips seem harder to source. LCSC currently only has one option in stock. If you go to LCSC to buy the PY32, you'll find 4 options of the F0 variant available. F0 here just means that they're Cortex M0 Plus parts. The higher the part number, the more features you get, and also the more you're going to pay. The F002A, the cheapest part, can run up to 24 megahertz, has 20 kilobytes of flash, 3 kilobytes of SRAM, up to 18 I/O, 1 analog to digital converter, 3 timers, and 1 each of SPI, UART, and I2C. Notably, it does not have direct memory access, DMA, or a real-time clock. The F003 adds the DMA and the real-time clock, and it allows operation up to 32 megahertz. It also has more flash and RAM, and an extra UART. But expect to pay more. These start at 14 cents. Talk about pricey. Going up to the F030 gets you all of the above, but now with 6 user configurable timers, an extra SPI bus, 32 kilobytes of flash, and 4 kilobytes of RAM. These can be run up to 48 megahertz, and you even get an internal phase-locked loop to produce this frequency from the internal high-speed oscillator. These will set you back around 30 cents. And finally, the F072, the real powerhouse. 128 kilobytes of flash, 16 kilobytes of RAM, running up to 72 megahertz with 10 timers. You even get a DAC. And for connectivity, 4 UARTs, 2 I2C, 2 SPI with I2S for audio, 1 CAN, even USB. There's a 64-pin package option available that has 58 I/O. These do cost around 50 cents if you're buying 500 though, and that's pushing the RP2040 territory. So I personally think the lower end of PY32 parts, the really cheap ones, are the more compelling candidates. Now I've read that the F002 and the F030 are actually the same die inside, and if you know what you're doing, you can uncover that extra memory, the PLL, and the higher clock speed, the DMA, the other peripherals. I haven't verified this, but I'm planning to build some general purpose boards in the future, and I hope to check this out. To develop code, program, and debug these devices, you'll want an integrated development environment. Choice of IDE is hugely opinionated, but in an effort to get the PY32 up and running as quickly as possible, I chose to use Kiel Microvision, as Puya devices directly support this. There are other IDEs you can use. I've seen people using STM32Cube IDE even, and there are other tools included with the documentation, but I've yet to explore these. Besides an IDE, you'll need something to program with. I found that my generic ST-Link v2 works well, and I've put an affiliate link in the description for these. There are lots of other options out there as well. You can even make debuggers using common microcontroller boards. You're also probably going to want something for serial communication with a computer. I'm using a second ST-Link, a V3 in this case, but any RS-232 serial adapter will work fine. You're probably also going to want a PY32 microcontroller board to check out your code, and this is perhaps the trickiest part. Puya has start kits available that are really nothing more than a chip broken out to the pins, with a crystal, a regulator, and a couple buttons. There's no onboard programmer or debugger. When I bought my PY32F003 version, this was about 3 or 4 months ago, these boards were $5 each, but now they're up to $18.50, which is frankly ridiculous for what you're getting. Obviously, if you're wanting to check out the PY32, paying $18 is way easier than trying to spin your own board. But come on, $18 for a 10-cent microcontroller? Regardless, I'll be using the PY32F003 start kit in these examples. So to get started, download and install MicroVision. There are free versions available straight from ARM that are plenty sufficient. Also, you're going to want to get the documentation zip file from Puya, extract it, and just have a poke around in there. Now, MicroVision does not like Chinese characters in the path name, so use this opportunity to rename them anywhere you see them. When you open MicroVision, the pack installer should automatically load. If not, open it. Wait for it to update, and Puya should appear on the left-hand side. Drop the menus down, find the appropriate device, and then click Install at the top of the right side. And that's it for installing the pack. Now, create a new project in MicroVision. In the dialog, select the appropriate pack you've loaded. I'm using the Puya PY32F003X6 here. You're also going to want to select CM Syscore and the device startup. Now I'm going to load the template code that Puya provides in their documentation. Go to Libraries and Examples, and then drill down to Templates. Select your board, and you should find source and header files. There will be a main source file and a main header, an interrupt source file and header, a HAL MSP source, and a HAL config header. You don't need to recopy the system source file. MicroVision already has it. I recommend copying these files to the local project folder, since you're likely going to be changing them. I'll put them in Objects. In MicroVision, right-click on the source group and then choose Add Existing Files to Group. Then navigate and load the appropriate files you just moved over. Next, we'll need to set the defines for the project to tell the code which microcontroller we're dealing with. Right-click on Target 1, then choose Options for Target, go to the C/C++ tab, and enter your microcontroller into the Define box. I'm using the PY32F003X6, so that's what I'll put here. While we're here, there are a couple of include paths you might want to add. The first is just to the Objects folder within the project directory. The second is for the header files for the HAL drivers. We'll cover this more later, but just open the stuff you downloaded from GitHub, navigate the path I'm showing here, and click the Include folder. Finally, under the Debug tab, you can select the debug probe you're using and configure any other debug settings you might want. I'm using the ST-Link V2. Now, since I want to use the HAL drivers, I'm going to create another source code group and add the HAL driver source code. There may be an easier way to do this in MicroVision. Let me know if there's a better way in the comments, but what I'm going to do here is simple enough. I'll just add existing files, then navigate to Libraries and Examples, click through, then Drivers, and PY32F0XX_HAL_driver. Then I'll go to Source. I'm just going to add all the HAL ones and skip the low-level drivers. You could also only grab the ones you need if you're so inclined. Okay, now that everything is set up, time for a couple of quick examples. First, the Hello World embedded devices, blinking an LED. I'm going to do this with a timer and interrupts, rather than delays, since delays lock the processor while they're executing. First, I need to configure the output pin that drives the LED. Looking at the schematic for this board, the LED is connected between pin PB5 and VDD with a current limiting resistor. I've written a function to initialize this. I'll just set the pin, set it push-pull, pull it down, and initialize it on port B. I want the LED to toggle periodically, so now I'm going to set a timer with that period. I'll create a timer initialization function, and for this one I'm going to use timer 1, which is an advanced timer. I'm not going to get into timer setup in depth, but I want this to trigger 4 times a second, or every 250 milliseconds. Running the clock at 24 megahertz means I want the timer to trigger every 8 million cycles. So I'll set the period to 10,000 and the prescaler to 800. These are zero indexed, so be sure to subtract 1. You can search STM32 timer setup to get more information on this. Now I'll just call the initialization function, make sure to use the interrupt version, that's what the IT here means. Also, don't forget to go into the HAL configuration header and turn the timers on by uncommenting the appropriate define. Now I need to tell the microcontroller what to do when the timer interrupt triggers. This code needs to go in the callback handler for the timer, this function here. Every time it triggers, I simply want to toggle the LED, so I'll use the GPIO toggle function. I also need to add a function to the interrupt file, the PY32F0XX_IT file, to handle the interrupt as shown here. Make sure to add the prototype to the header file as well. For clocking, I'm going to change the default 8 MHz to be 24 MHz, just by changing the HSI calibration value. Lastly, I'll go to the HAL_MSP file, and I'll add this HAL_TIM_BASE_MSP_init function. This is going to enable the timer clock, as well as configure and enable the interrupt. Throw the two initialization functions into the main function, and that should be it. Let's flash the code. Two little hints here. One is that even though the part will run at 5 volts, I cannot get the code to flash at that voltage. To program the parts, I'm using 3.3 volts as generated by the ST-Link. The second thing is that the microcontroller needs to be restarted after flashing the code, and this isn't automatically done, at least for me. There's a reset button on the start kit, or you can just unplug and replug. So load the code, done, reset, and there we go, flashing light. Okay, now I'm going to do something slightly more interesting. I'm going to use the internal ADC to read an analog voltage coming from a potentiometer. Then I'm going to send the resulting value to a computer over the UART peripheral. This is the exact sort of thing you'd do if you were making an analog sensor into a smart one. The first thing I did was write 3 configuration functions. Let's start with the GPIO. I looked at the datasheet and found UART2 on pins PA0 and PA1, which is alternate function 9 for those pins. I put the struct together, and I initialized it. I separately set up the ADC using channel 2 on pin PA2. I set it to analog, and I initialized that one as well. Next, the UART. I'm going to set everything up fairly standard as far as bits are concerned. I set the baud rate to 115,200. Any standard value should be fine here, just make sure your receiver is set the same. I then called the UART initialization function. Finally, onto the ADC. There's a lot of configuration that can be done here, but without going into too much detail, I'm just going to do 12 bits, a single conversion, software start, 41.5 cycles per conversion. I'll call the ADC initialization function. Next, I need to set the rank. I'm going to set it to the highest, and then I'm going to set the channel to channel 2. Finally, I'll call the appropriate configuration function. If this is looking unfamiliar, there are lots of other tutorials online on setting up the ADC, or just reference the STM32 HAL manual. Now, I'll head over to the main function and get everything working. First, I'm going to call those 3 functions I just wrote. Now I'll call the ADC in polling mode, and I'll save the value to a variable. Once I have the binary value, I will go ahead and convert it to a string. I'll then concatenate it with some other text so that it reads, the ADC value is blank. Now just call the UART transmit. I'm just going to do this in blocking mode. Finally, I'll add a 1-second delay and then have this just repeat over and over. For circuit setup, I'm using a potentiometer with the center tap run to the ADC pin. I've then run the UART to an ST-Link V3, which has a serial transceiver built in, but any USB to serial adapter should work fine for this. I've opened a serial console in MOBA Exterm with the appropriate baud rate. Now I'll just flash the code, reset the board, and there we go. As I turn the potentiometer, the reading increases and decreases as it should. There are, of course, other peripherals built into this thing, but there are a couple of places you can go if you need more help. For one, The example code provided in the zip file from Puya is very useful, and it covers pretty much every peripheral. There's also a well-written reference manual for the F030 in English, although don't expect step-by-step guidance. Finally, these parts are really similar to STM32 parts. I dare say Puya borrowed a little from ST. Therefore, the STM32 HAL manual is directly applicable, and it goes into great detail. I've been using the one for the STM32G0 series, which is also a Cortex M0 Plus core. Little hint here, not all of the features available on the STM32G0 exist on the PY32. So if you're configuring a peripheral, start by typing all of the configuration parameter names in MicroVision. If it doesn't attempt to autocomplete, then it probably doesn't exist on the PY32 chip. If you do type it all the way out, and it doesn't exist, it'll also throw an error such as no member found. That's pretty much all there is to programming these. If you've coded Cortex M0 Plus or other similar parts before, you'll find this very familiar. There really aren't any surprises. The hardest part, honestly, is probably designing a circuit board and soldering the chip to it. I've posted both of these simple projects to GitHub, linked in the description. If you've got any specific questions, go ahead and post them in the comments, and I'll do my best to answer them. That's all I've got today. If you found this useful, please like and subscribe, and go check out my other videos where I put the PY32 to use. Thanks for watching.